Hi, welcome to this lesson on number patterns, sigma notations. Here we're going to be looking at properties of sigma notation, and we're going to be looking at the sum law. So let's have a look at this property of the sigma notation, which we call the sum law. It basically says the following. In shorthand notation, if you take the summation from I equals 1 to n of a sum of two general terms, so instead of just normal ti, which we usually had, we now have two general terms. We have ai and we have bi. So if we expand this sum out, what is it saying? Well, it says that if you take the first index I equals 1, then this becomes a1 plus b1. That is the first term of the summation. Then the summation symbol says you now add the next term, which will be a sub 2 plus b sub 2. Then you add the third one, a sub 3 plus b sub 3, all the way up to this very last one here, which is stopped by the upper bound, little n, and that is a sub n plus b sub n. Now, because addition is what we call commutative, which just means you can switch the order of how you sum things. For example, 3 plus 5 plus 7 is the same thing as saying 7 plus 3 plus 5. It doesn't matter that I switch the 7's position to the first term. If you're adding numbers together, then you can add them in any order. That is the commutative property of addition. So we're going to move all the a terms to one side in a bracket. So a1 plus a2 plus a3 all the way up to plus an. Okay? Then plus b1 plus b2 plus b3 all the way up to bn. But this is very long notation, and we know that there's a shorthand compact form for it, which is the summation notation. So the sum of a1 all the way up to an can be written as sigma, the summation of I equals 1 to n of little ai, plus the summation from b1 to bn, so from I equals 1 to n of bn. So what does this property say? Well, it says that basically if you have a sum of two general terms, ai plus bi, where I ranges from 1 to n, you can break it up into two summations. Summation from I equals 1 to n of ai, plus the summation of I equals 1 to n of bi. Okay, but this actually does work as well for the summation from I equals 1 to n of ai minus bi. And you can actually break that apart as the sum from I equals 1 to n of ai minus the sum from I equals 1 to n of bi. You can prove that same structure here by using this exact same argument that we've done here in this box. So let's have a look at an example of how this is applied. Let ai be 3i plus I squared. Well, rather ai just be 3i and then bi be I squared. Then if you add them, you get ai plus bi, which will give you 3i plus I squared. And let n equal 3. So if we want to sum the first three terms of these two different sequences, we can write it as follows. The sum from I equals 1 to 3 of your ai, which is 3i, and your bi, which is I squared. Now, if you sum this by looking at that as the whole general term, wherever there's an I, you replace it with a 1. So that's what I've done here. For the first one, it's 3 times 1 plus 1 squared. Then you got I equals 2. So this is I equals 1. This is I equals 2. That'll be 3 times 2 plus 2 squared. Then you sum up to the next term, which is the last term. I equals 3. 3 times 3 plus 3 squared. And doing that arithmetic, we'll see that we'll get 4 plus 10 plus 18, which gives us a sum value of 32. But if we did it the other way and we broke it up into individual sums, so the sum from I equals 1 to 3 of 3i, plus the sum from I equals 1 to 3 of I squared, then for the first term, for this first general term here, I equals 1 is here, I equals 2 is here, and I equals 3 is here, and you substitute those I values for 3i. So 3 times 1 plus 3 times 2 plus 3 times 3. Then you do the second summation, which says from I equals 1 to 3, you're going to square it. So at I equals 1, you're going to square 1. At I equals 2, you're going to square 2. And at I equals 3, you're going to square 3. So doing it that way, we're going to get this sum here, 3 plus 6 plus 9, for the first general summation. And then the second one will be 1 plus 4 plus 9, which gives you 18 plus 14, which is 32. Exactly the same answer. So why is this useful to know? Why do we want to break up summations like that? Well, there's going to be sometimes nice general formulae that you will know of, such as the arithmetic series or the geometric series, where it might be easier to break it apart and then use the sum formula that we've learned for arithmetic and geometric series. So that's where the sum law will come in handy when we need to use it. All right, I'll see you in the next one.